Hey guys, so we're just going to go ahead and finish up the section of notes that really kind of introduced a whole new group of numbers. And they're pretty important for solving questions where we don't have a real number. And we were just starting to learn how these new imaginary numbers work. And they're all based on basically taking square roots of negatives, which shouldn't be possible, but when we're dealing with this new type of number, if you square that amount, then you end up with a negative result. And so they work very similarly to our normal square roots. And so you can see with questions 11, 12, and 13, basically it's the same process of you break them down and pair them up. The pairs go outside. Anything left over that is a single that doesn't have a buddy gets to go inside as 2 times 11 or whatever it would be, and you multiply those things up, and the only difference is that you put the letter I afterwards. And so the next step of this is really combining these imaginary numbers with regular numbers and forming what is actually called a complex number. Complex numbers are the real deal. They're super powerful and super useful. All complex numbers can be really written in this format, a plus bi. And if we talk about the a part right here, this is a real number. So these would be any of the normal numbers that you were used to before last week rolled in. It could be like 7, it could be 17.3, it could be a fraction like 2/3. Negatives are real numbers as well. So it's any number that you have seen up to this moment in your math career. Then the bi part is the imaginary part. This is an imaginary number. So several examples of this, if you just came up with numbers on the spot like 14, and I'll make up another number, how about 8? 14 plus 8i, that whole thing is a complex number. So it's like a team, it's a partnership between a real normal number and then one of these imaginary new numbers. You aren't limited just to adding, so let me come up with another amount, 10, but we'll subtract 2i this time. That is also complex. Both of those teammates work together. You can even have 4 plus I. We understand that there's one of those i's, and so not putting a number in front of I just means that there is a single I. So that brings us down to question 14. Which of the following expressions would be considered a complex number? The first one actually is not. So 21i is just imaginary. There's no real part that goes with that. 6 minus I, its neighbor, is considered complex. It has the real part, and it has the imaginary part. There's one of those i's. 3x plus 2i. That is not a complex number. The x part of this actually makes it a little bit bigger than a number, a little bit too complex to be a complex number, if you will. 9i plus 0 is perfectly fine, but it's written backwards from what you would normally see. 0 plus 9i is probably the more accepted way to write those two numbers that are working together. 4i minus 8 is the same idea, but you got to be careful about writing this in the correct order. 8 has to be negative. The sign goes with it. 4i is positive, and so it would be negative 8 plus 4i. This would be the real part, and this is the imaginary part. Negative 3i is imaginary. Doesn't have a buddy in front to make it a complex number. And then I plus 21 is complex, but we would most often see it as 21 plus I. So that takes us down to 15. Now that we're a little bit more familiar with how complex numbers look, can we simplify the following complex numbers and put them in this standard form, this a plus bi form? So firstly, we have to take our square roots and break them down. 18 is 9 times 2, 9 is 3 times 3. I have a pair of 3's and a singular 2. Don't forget, I like to circle the negative and draw a little arrow because I need to remember that this is an imaginary number. Otherwise, this pair of 3's goes outside, the individual 2 is left inside, and don't forget the I, it goes after this square root, so make sure that you are not putting I under the square root there. And then I can't forget about this 7 in front. Typically, those regular numbers like to go in front. That's the A part of A plus BI. This funky looking thing is my complex answer. Please never, 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 never do this. Taking 7 plus 3 to get 10 root 2I. That would be absolutely wrong because we have to multiply those things, and not only do we have to multiply before we would ever add, but this is imaginary, and imaginary things do not combine with their real counterparts. You can almost think about it like having an imaginary friend. They never combined with you, you kept separate. The central question, -5 plus the square root of -121, actually negative 121, breaks down into just 11 times 11. I suppose we could show our work. This will become I. So the square root of 121 is simply 11, I, and then -5 is in front. The 11I was positive, so we'll make it plus 11I. And then lastly, square root of -5. Technically, this is just an imaginary number. If I wanted to make it look a little bit more complex, I can add 0 to things and not really change how much is being seen here. So 0 plus the square root of -5 is the same amount. Really about the only thing I'm going to be able to do is change the square root of a negative into being an imaginary number. So this would look like, in the end, 0 plus root 5. The square root of 5 stays as square root of 5, I. If you are interested, square roots as their values are often really gross decimals, and so the square root of 5 here is about 2.23i. Just like you can have 1i or 11i, you can have these gross decimal amounts of I, just like you can have negative amounts of I. It's a number, and you can have all sorts of amounts of this number. Hopefully that gives you a little bit of practice with just dealing with them, dipping your toes in the water, because if we move on to the next page, we're going to learn how they add together, how they subtract and multiply, just like you can do that with normal numbers. We're going to do it with imaginary numbers and see some of the interesting quirks that happen. We will be doing everything except for division with complex numbers. There's some special things you have to kind of do when you divide by groups of things, A plus BI, and so that's why we're just sticking to some of the basics. So 16 here, 4 minus 6i, that is a group, that is technically a complex number, because it's the pair of them, plus 3i, this is just an imaginary number. And so when we add those together, we just have to find terms that are similar. I, when it comes down to it, it's basically a letter. You treat it like a letter. I mean, it is a letter, but it's standing in for a number as well. So the similar terms here are -6i and 3i, just like how if you had -6x plus 3x, those would go together. The 4 that would precede it does not go together. It's not a like term. So this makes -3i, and 4 is chilling like a villain in front, and that is it. Please be aware, do not combine these two things together. You have to know when to stop. So this answer here at the end is a complex number. Let's go ahead and let's try 17. I have 8 plus 3i, it's a complex number, added to 2 minus 4i. So if I'm looking through for like terms, 8 and 2 definitely can go together to make 10. The 3i added to the -4i combined to create -1i. Now if I wanted to, I could just write this as 10 minus I, and that's perfectly fine. Got to be careful if you're switching around the order though. This would be negative I in front plus 10. Typically, I don't write it with the imaginary part first, but some people write it that way just because that's what they look at first. Okay, just make sure sign is going with it. 18 is interesting. If I'm looking at this, negative 1 plus I added to negative 2 minus I. The negative 1 and the negative 2 is pretty easy. They make negative 3. But it's the positive I and the negative I that if I add those two things together, I get 0I. So negative 3 plus 0I is really just the same thing as negative 3 plus 0, and that results in negative 3. So sometimes taking a complex number and adding it to another complex number can lead you to a result that is actually a real, normal, regular number. If I told you about negative 3 degrees Fahrenheit, you'd be like, oh yeah, that's totally a thing. And this is totally a thing, even though it came from two types of numbers that seem weird and awkward and new to us. And I think that's pretty cool. So maybe summarize. 16, 17, 18. All of these questions were adding in between those groups of things. And so if you ever need to, or if you come across in your homework questions that are adding, this would be a great spot to come and reference. Okay, and it's going to be a little bit different for 19, 20, and 21. These questions actually are all subtracting in the middle. You have to be particularly careful about subtracting groups of things. If I'm subtracting 2 and this negative 4i, I have to take that negative sign and distribute it to everybody, because it's pretty simple just to subtract 2, but when you subtract the negative 4i, or subtracting a minus 4i, it actually becomes positive 4i. And so distributing the negative basically takes care of the trick for this problem, and we can just combine the things together that go together after this. So 8 and negative 2, that makes 6. 3i and 4i, that's going to make 7i. Keep in mind, don't combine these things. That is where it finishes. Let's go ahead and let's take a look at question 20. If I take the negative here and distribute it to the 3, that will be minus 3, and a negative times plus 2i is minus 2i. 7, still chilling in front. And so I can take the 7 and the minus 3. 7 minus 3 is just 4. Subtract 2i afterwards. And that is my final answer. And so the mathematicians that were all pretty skeptical of imaginary numbers and complex numbers, they started to buy in a little bit once they saw how intuitive it was and how easy it could really be. And so this really opened up a whole new field of things you could do in math, because we have some more tools at our disposal, some numbers that are useful. So question 21, taking that negative sign and distributing, will make the problem look like this. 3 plus 6i, subtracting 4, subtracting a negative 8i makes it plus 8i. Combine the terms that go together. 6i and 8i make 14i, and then 3 minus 4 make negative 1. Negative 1 plus 14i is where this question finishes. Alright, so these questions, if you ever need to go back, are all subtraction questions. So not too hard. The last piece of the puzzle is how to multiply. Okay, multiplying complex numbers is maybe a smidge trickier, but it's not something that you haven't done before. And in fact, it involves kind of a fun acronym to make sure that you are multiplying all the pieces together that need to go together. So because complex numbers have two parts in them, so first part, second part, a plus bi, and then you could potentially be multiplying by a second group, a third thing, and a fourth thing, a plus bi again, you need to make sure that everybody gets multiplied everywhere. And so this 1 needs to get distributed both to the 3 and to the 4, okay? And so there's a nice way to make sure that we aren't missing any possible combinations of these things. And so it's a 4-letter F word, which be careful what 4-letter F words you say in your head, but it's FOIL, which just helps us to remember we need to multiply the first things together. So 1 times 3, they're the first things in each parenthesis. Then you're going to multiply the outside things together. And that would be 1 and 4, the outer part of this whole problem. I stands for inside. So 2 multiplied to 3, they're both in the interior of this problem. And then L stands for last, and that would be 2 times 4. And so you can kind of see when I underline them, everybody's got 2 underlines because they're all interacting. Basically, you took 1 and distributed it twice, and you took 2 and you distributed that twice. Okay? One thing that will be important, this is a very big deal with these problems because they are complex. I squared will show up quite often. And we have to remember that I squared is equal to -1. That's the whole point of why imaginary numbers exist. So that lets us actually go a step further. If I squared shows up, we can usually combine it with the other real numbers that are hanging around. So let's try 22. We're not FOILing yet. We actually are just taking 6i, this imaginary number in front. We're just going to distribute it into the group. So 6i times 8 is very similar to if I had 6x times 8. You take the 6 and the 8, and you multiply those to get 48, and the letter is just hanging along with that coefficient. Then we take 6i times -3i. So -3 times +6 makes -18. But if I have an I times an I, just like if I have an X times an X, that is when we get X squared. So those are 2 big important rules. But our letter is I, so I end up getting I squared. Now, remember that little hint that we just talked about? I squared is equal to -1. So we can just go ahead and say this is minus 18 times -1, or in the end, plus 18. 48i, you can put that in front. I don't technically really like it up there. I think it would look better if we had the real part first, and then the imaginary part. So 18 plus 48i, I think is how most math textbooks would write it. And there is like a graphic reason why we do this as well. The real part gets taken care of first when we start to visualize complex numbers, and the imaginary part gets taken care of second. So what about 23? 23 is actually super interesting. That's 4i times 4i. And another way to really think about this question is 4i squared. And the numbers that we know, if we square positive things, we end up with positive amounts. If we square negative things, we end up with positive amounts. Squaring stuff with our numbers ends up positive. But what happens when I square this imaginary amount? It's pretty easy. Taking 4 times 4, you get 16. And then just like how we got I squared in the last problem, I times I here, it's I squared. But we all know 16 needs to get multiplied by -1 because I squared is equal to -1. And so the result of taking this imaginary number and squaring it is -16. You just took something, multiplied it by itself, and ended up with a negative, which was impossible to us just a few days ago. But now that we have this new useful number, we can end up with this result, which is beneficial sometimes. We need it. So 24 is very similar. We just are going backwards. If we take 4i and 12i and multiply those, we get 48i. And then 12i times -2 is minus 24i. And actually, as I was writing this out, I and I would continue to interact together, but I realized I missed taking I times I to get I squared. And so actually, this first piece is 48 times negative 1. They shouldn't interact because they are not the same size for their imaginary number. 48 times negative 1 is negative 48 minus 24i, and that is it. If we go ahead and take a look at 25 through the end, these are the bigger questions where foiling starts to take a bigger role. So having 6 times 4, the first things in our problem, 6 times 4 is 24. Then if we're going to go ahead, we're going to do the outside of this problem. 6 times negative 3i is minus 18i. Now we can go ahead and we can do the inside. So negative 5i times 4 is negative 20i. And then we have negative 5i times negative 3i, which is plus 15, and then I times I makes I squared. I won't make that mistake again. So now we can go ahead, and if we're looking, it seems like I have some like terms I can combine. Negative 18i and negative 20i make negative 38i. 24 is still in front, but then I'm not just adding 15, I'm adding 15 times negative 1. That's the identity that we have to know. So really that's subtracting 15. And if I combine the 24 and the minus 15, that one last step leaves me here at 9. 9 minus 38i. Awesome. 26, if you look at the two complex pairs that we are multiplying together, they seem almost the same. They only differ really because one is plus and one is minus. We're still going to go ahead and FOIL. So these are the little distribution arcs that I need to be following. First, 2 times 2 is 4. 2 times negative I is minus 2i. Then I get plus 2i from the inside. And then I positive times I negative is minus I squared. So these two things actually cancel out to be 0i. So we don't really even have to think about them. The 4 is still here though. And then I'm subtracting, if you remember, I squared is negative 1. So I always go ahead, and I'm very careful, I put negative 1 inside parentheses because subtracting that amount actually makes it adding. So 4 and then adding 1. 4 plus 1 in the end is 5. So this is actually super strange. The fact that I took a complex number, multiplied it by another complex weird pair number, and then I end up with a real number. 5 is a very normal amount. Very interesting, very strange that these imaginary numbers can end up at a number that we are so comfortable with. And without further ado, the very last problem, 27 here, 2 plus I squared. I often see a very simple mistake of taking that squared and trying to distribute the squared. And I will show you why that does not work, just with a couple of numbers. I'm going to pick out 2 and 7. You can always test some of these little hypotheses by putting some numbers and playing around with the numbers. So this is why distributing the squared is impossible. It doesn't work this way. You get 2 squared plus 7 squared, 4 plus 49, and that is 53 in the end. Okay, 53 we're going to see is totally wrong because you technically should add the things inside the parentheses first. Parentheses and grouping signs are most important. We get 9 squared. 9 squared is equal to 81, and so these things are definitely not the same. So please never distribute the exponent. Exponents essentially cannot go across an adding or a subtracting sign. They just don't work like that. So what do we do? Well, I think the First thing we need to think about is what it means to square something. It just means we have two of them multiplied by each other. So they're like clones sitting next to each other. And the moment I write them out as a double times a double, you should be able to see that we're just going to FOIL. It's that same process. So getting 4 plus 2i, the inside and the last here will be another 2i, and then plus I squared. So these two 2i's can create 4i. That's what you get when you add 2 plus 2. Crazy. Plus, this is a negative 1. You could just say subtracting 1 if you wanted to. And then the original 4, we're going to bring it down. 4 eventually added to negative 1, create 3. And don't forget to keep that 4i in your answer. So imaginary numbers, not as hard as they maybe seem. They still probably feel a little uncomfortable to you, but that's okay. The more you work with them, the better off you will get. So why the heck do we even have imaginary numbers? What are they good for? And you might be interested to know that lots of things use imaginary numbers when they were being designed and engineered. Anything that has flow or oscillations, it is much easier to solve if you use complex numbers and imaginary numbers. So there's kind of a picture of, water flowing around a post or something in the ocean, and so it would create these little vortices, and it could be high pressure, low pressure. All of those things, imaginary numbers, play a critical role with just where things are and how they behave and predicting what will happen. It's really fascinating. The picture here over on the left is the bean up in Chicago, and how the grid of pavers is reflected off of this curved surface of the bean. Actually, you can predict that with complex numbers. And so it's super interesting how a number that was insulted and called imaginary, like it didn't exist, actually turns out to be a pretty critical part of modern life. Airplane wings even use complex numbers to decide the curvature of air flowing over versus under the wing. And yeah, I think that's really cool. At the bottom of this is a little bit about how imaginary numbers are actually graphed. They're graphed as a vector, which, if you don't know what a vector is, that is okay. Basically, it's just an arrow pointing to a certain location in space. But it involves the regular numbers along the x-axis and the imaginary numbers along the y-axis. And so that's how they get combined together. And that's why we typically go real numbers first, because they're like x values, and imaginary numbers second, because they're kind of like y values. All that being said, I hope you guys kind of enjoyed these notes. Please be practicing on the homework, and if you have questions, don't feel hesitant to reach out. I'd be more than happy to help. Thanks, guys. I hope you have a great day, and we'll see you guys later. Take care.